So first of all, let's talk a little bit about these higher level business concerns. Firstly, there's customer experience, right? You want to have a product that keeps your customers happy, right? Everyone wants happy customers. Probably the business wants happy customers because they keep on paying for your product. It's also really good as a developer of a product, right, to have customers who are happy. It's motivating from your point of view as well. And one of the things you really want to make sure for those things, it's not a slow product. It really drives me nuts when I'm waiting for a website to load and it takes ages for it to load. So having happy customers, performance is part of that customer experience. Then there's the fact that responsive applications make you more money as a business. Now, I live in London, and when you talk about this to software developers in London, they always think of things like really low latency applications, high frequency trading use cases, for example, where people are always very, very focused on the performance, and there's like a direct link to money. But you've worked in other problem domains where that's the case as well,
I used to
right?
work in ad tech, and if anybody's been in ad tech and been around RTB, real-time bidding, there you have these auctions that happen every time there's an ad request. You have 140, 150 milliseconds to return your bid. If you miss that time window, you're not part of the auction. If you miss too many auctions, you're thrown out the exchange, and you basically have no business.
Absolutely. But even in more regular development environments, maybe you've got a website, you've got some customers who are looking at that website, responsive websites can rapidly make more money. Amazon released some numbers saying that 1%, that 100 milliseconds of latency on loading their Amazon storefront cost them 1% of sales, okay? So that's a huge number if you're somebody like Amazon. That's only 100 milliseconds in terms of time. That's really, really fast in terms of a very short delay that you're adding there, and it's already costing you money. Google released some numbers as well. Again, they did an A/B study on their search homepage, and they added half a second to the load time of that page. They basically just had some of the requests take half a second longer, and it dropped traffic by 20%. That's huge, right? A 20% drop in traffic for half a second delay. That's very, very expensive, especially if you're having to pay to acquire those customers through some existing mechanism or online advertising and stuff like that. Really increase your business costs elsewhere. And what's the takeaway there? Well, people are pretty impatient, to be honest. I mean, I know I would be when I'm looking at web pages. So responsive applications make more money. You also want to think about downtime as well. A lot of organizations have downtime or situations where their system stops working when they're under heavy load. Okay, I'm sure we've all experienced this at some point in time. And that can cause downtime for your business. It can cause either actual outages or effective outages where the software is unusably slow or unreasonably unresponsive.
Yeah, and it's worth pointing out that performance interplays with system reliability as well, where your bottlenecks in your system when you're not at full load can quite easily turn into production issues when you suddenly hit full load, right?
Absolutely. So who here uses Facebook to talk to their friends and colleagues? Okay. What about WhatsApp? So who uses Friendster? No one. Why does no one use Friendster, Sadiq? Didn't you used to love Friendster?
Yeah, we're kind of exposing our ages here.
Yeah.
I used Friendster when I was at university, and it was a social network, a bit like Facebook, but maybe slightly earlier on. And they couldn't scale. They were growing like a weed, and I remember many evenings trying to kind of get F5, trying to actually get the page to load eventually, and it didn't. And actually, their inability to scale up their system cost them what could have been a couple of $100 billion opportunity. Absolutely, absolutely. And finally, there's reducing costs. Now, I don't want to say all costs are infrastructure costs. That would be a bit of a fallacy. Obviously, developer time is quite expensive as well. But these days, infrastructure costs are increasingly measured and metered. Things like moving to the cloud means your cost base for your infrastructure isn't a fixed cost concept anymore. It goes up as you use more CPU, as you use more memory, as you use more disk space, as you use more network traffic, right? So if you can cut some of those infrastructure costs, especially if you're operating at scale, where those infrastructure costs also scale up, then you can often save your business a bit of money as well. So that's great. Cool. So when people think about understanding the correctness of their application, like
testing, they'd often jump to unit tests in development. And if you're thinking about understanding the performance characteristics and saying, is your application performing okay, you might do the same thing. See, hey, can I just write some performance tests for my application? But that can often be a bit of a challenge, can't it, right, Sadiq? So what's the problem with development environment performance testing?
Sure. So over the next few slides, we're going to talk about why, from a performance point of view, development is not representative of production. So our goal here for performance work is to reduce the load in production. If we're reducing performance bottlenecks and increasing our capacity in development, well, that's nice, but not really that useful. The end goal is to increase capacity and improve performance of production. In the next few slides, we're going to see why performance testing in development is not representative of production, right? Why we may actually end up with the wrong conclusions, end up doing the wrong thing. So why do people do performance testing in production, in development? Well, for one, it's a lot easier. So the tools that we have access to are generally, the profiling tools we have access to and performance tools we have access to are generally designed to work in a desktop environment, right? So they're much easier to use if you have the application running locally. You don't have to mess around with firewall rules or figure out some complex remoting protocol. You may not also have access to production. Like in many organizations, that just isn't a thing. But over the next few slides, we're going to see why doing this is a bit of a trap, why we might end up getting the wrong results. So the first thing is that the hardware that we have access to in production is very different to the hardware we have access to in development, right? You might be running on a 32-core or 24-core Xeon Gold in production, but you might actually have a 2 or, if you're lucky, 4-core laptop that is optimized for very different things. So in production, we're optimized for throughput, whereas on your laptop, you most likely have something that's optimized for power consumption. And so CPU is different. So other things like your memory subsystems are different numbers of memory controllers, memory bandwidth, I/O subsystems. Again, on your laptop, you likely have an I/O subsystem, SSDs that are optimized for power utilization, whereas on servers, they're going to be very, very different. And by optimizing for what your laptop has or your development environment has, you're actually likely to be chasing different bottlenecks than you are in production. So for example, if production is a 24-core CPU, you're far more likely to actually encounter concurrency-related issues like lock contention and deadlocks and such like on that environment than you are on a 2-core or maybe 2-thread, 4-thread laptop CPU.
Recently, we've had a couple of organizations come up to us at Opsian and ask, do you support IBM mainframes? And we're like, wait, IBM mainframes in 2018? They're like, yeah, we still use them. They work great. Fair enough. We don't actually support that, but it shows that there are some organizations who have even bigger differences between where they're running their production system on and their development environment than just, say, a different version of Linux or a different Intel CPU.
Sure. So who here runs the same software on their development environment as they do in production? So same operating system, system libraries, and everything else. I see a couple of hands at the front. Right. In organizations I've worked in recently, I've actually seen that a lot of the time we don't even run the same operating system as we do in production. Like a lot of development happens on Macs and deployment happens on Linux-based machines.
Or development on Windows and deployment on Linux-based machines.
But as we've seen in the last few years, especially for things like the Spectre and Meltdown mitigations, even small differences in operating system or system libraries can have a very different effect, can have a very dramatic effect on performance. So if you look at the patches for Spectre and Meltdown, even just different versions, small versions of Linux kernel had very different syscall performance.
And on Windows, it's the same as well. There was a patch release that was just a regular Patch Tuesday update back at the end of March of this year that slowed UDP throughput on Windows down by 40%. That's huge, right? 40% slower UDP throughput. That was, again, one of the Spectrum Meltdown mitigations, I think, that was kicking in.
Sure. And then the next thing is unrepresentative workloads. So what do we mean by workloads? So workload is the way in which a system is exercised. So your production workload is hopefully your end users, whether they are people or other systems, requests against your production environment. So that's what I mean by a workload. Workload is a way of the system being exercised. So even if you have an environment which matches your production exactly and then has exactly the same software as well, it's very, very difficult to actually create a workload that exercises it in exactly the same way as production is exercised. So there are some basic things you can know. So you can say, all right, well, I will create a synthetic workload, all right, and then you start asking questions about the synthetic workload. Well, what's the distribution of requests across your endpoints? Well, that's reasonably easy to answer from things like logs. Okay, well, what's the distribution for a given endpoint? What's the distribution of requests between hot and cold data, like data we've got in cache, data we don't? A bit more complex to answer. Okay, what about the concurrency, the interdependence between requests? I once worked at a company where we had a misbehaving SDK out in the wild that would hit 3 different endpoints in our system, at the same time, and actually requested the same data and was writing to the same data. And so clearly that actually resulted in a bunch of concurrency issues that we would never have found if we'd actually just tried to create a synthetic workload that exercised our endpoints from what we thought users were accessing it in.
The other thing you can encounter with performance testing is one of these fighting the last war type situations, right? Whereby you have a problem, you create a performance test that realistically exercises the last thing you had, you fix it, you can repeat it, everything's good. And then you've got a different problem the next time round with a different set of behavior in production. So you can often maintaining these things is often very challenging as well.
Sure. And the last thing that we have in the Java ecosystem that makes things even more exciting and unpredictable is that the JVM does adaptive optimization. So what do we mean by that? It adapts the optimizations it does to the way that the code is being used. So if you actually have an environment that hasn't been exercised in exactly the same way as production, there's no guarantee that actually the optimizations that the JVM has done are the same as they've done in production.
I've seen situations where, for example, you have clustering systems that might fall over from a strong leader concept to a follower, and then when they fall over to the follower, they haven't been exercising the business logic in the same way on the follower as they have been on the leader. So as it falls over, the JIT compiler breaks a bunch of its existing assumptions, has to do a bunch of on-stack replacement operations, and immediately throughput drops massively, even though you've got a correct system and a correct new leadership election. So you can get these kind of problems as well, especially in a distributed systems setting.
Sure. So basically, the dog is cool, but you don't want to be the dog, right? Don't do your performance testing in development.
Absolutely. Cool. So having said we want to understand these performance problems in a production environment, what would we actually do to understand them? What can we measure? And the first thing that people jump to is metrics, right? So when I say metrics, I mean like some kind of pre-configured numerical measure, something you can pull out of a production system periodically. For example, how much CPU is being used at a certain point in time? What's the page load time of a certain request on a certain API endpoint? And you can take these metrics, obviously, and create any kind of pretty graph out of them. You can look at them. You can see what's going on. Metrics are very, very useful for narrowing down certain types of problems. They can let you know, for example, is an operation very CPU bottlenecked, or is it I/O bottlenecked? Is it actually that the machine isn't really doing very much at this point in time, and maybe it's another point in your system that's the problem? Metrics are cheap. So when I say cheap, what I mean is cheap to collect. The overhead of collecting those metrics on the production system is very low. And you do need to think about overhead, because whatever you're measuring has some overhead and it has some cost to it. And you don't want to be having high overhead production monitoring tools, because they slow your production system down and then become the problem. You're back to square one. Metrics can be quite effective. But the problem that people sometimes encounter with metrics is they get really hyper-enthusiastic and put metrics everywhere in their system, right,
Yeah,
Sadiq?
And then when something goes wrong, you end up kind of going through all the metrics and kind of pointing at this one and saying, are you responsible, are you responsible, are you responsible, basically until you find something that looks odd. And it ends up basically being a bit of a murder mystery kind of event. But
now, I know Hercule Poirot is meant to be originally from Belgium, but he's a fictional character, right? You don't want to be doing one of those murder mystery, point at all the different things and accuse them situations in a production environment when there's real customers on the line. Just want to understand what's going on more rapidly. So another approach you can look at is logging. Okay, there's a few different options you have in terms of logging. So firstly, there's kind of bespoke logging operations. So for example, taking some arbitrary record or event, something about the system, so measuring the time of an operation or the, say, how many threads you have in use in a thread pool or connections in a DB connection pool or things like that, and logging them out with your existing kind of systems like log4j, slf4j, logback. You can even aggregate these things. There's a bunch of tools out there for doing those kind of things. There's also a bunch of really useful tooling around logging for things like GC logs specifically that let you get insight into some specific JVM subsystem. Yeah. But logging isn't a panacea, right?
No, and logging is also especially interesting if you're doing logging from the point of view of performance, right? Because people often do logging from performance perspective, but then they don't think to actually instrument or actually test their logging's performance. And so a lot of the issues that we actually find are people realizing that actually, you know, somewhere deep in their system, they're actually not using asynchronous logging, for example. Or they are using asynchronous logging and they're actually blocking because the queues are too big or that kind of thing. And very rarely do people actually bother to actually performance test the logging they actually add to try and find performance problems.
Absolutely. Logging can often be the cause of performance problems rather than the best way to solve them. Also, if you are manually instrumenting code to add information into logs, that's time-consuming work that's eating up developers' time when they could be spent better doing other things. Then there's coarse-grained instrumentation, so bytecode weaving, things like that. What a lot of these instrumentation-based tools do is they add a bit of bytecode at the beginning of a method or something like that takes the time. They add a little bit at the end of the same operation that takes the time, subtract the end from the beginning, and then you've measured the amount of time that an operation has taken. Fair enough. Cool idea. Very useful. But the problem with instrumentation is the more fine-grained you want to narrow these problems down to, the more instrumenting code you have to add. And the more instrumenting code you have to add, the higher the overhead of this instrumentation becomes. If you want to do it for all of your methods, it'll be way, way too slow. You'll rapidly find you spend more time running your instrumentation code than you find you're running actual application code. Things like APM tools that do instrumentation-based approaches for production performance problems generally have a very coarse-grained approach to instrumentation. So they'll tell you something like how much time was spent inside the controller layer of your application, how much time did this SQL query take. So those things are useful things to understand. They can help you narrow down the problem beyond metrics, but you can't, the more detailed information, the more information you want, the higher the overhead and the bigger the problem there is there. Then there's production profiling, right? So production profiling isn't necessarily a technique that I think many people use today, but it is a viable technique in 2018 and something we can think about using. Profiling is a more general approach, so it just tells you what's eating up my CPU time. It just tells you general questions like this. It's just a way of saying what resource is being used by what bit of my application. So CPU time, what lines of code allocate the most objects. You can profile a lot more esoteric things. You can look at CPU cache misses. You can look at what's eating your memory bus traffic. All sorts of very low-level information if you want. Now, I think the first thing that people think of when they hear production profiling is, hang on, profiling is going to slow my actual application down in production hugely. I just can't do it. And we'll talk a little bit, that's partly true in many profilers, but we'll talk a little bit later on in this talk about how you can do it in a very low overhead way and how that works and how that problem specifically can be overcome. The other advantage profiling has is over other tools as well of having arbitrarily granular or arbitrarily deep information. It's automatic, right? You can just attach a profiler. You don't have to modify your actual application in order to understand things like you would do with, say, logging. Cool. Profiling also helps you find certain problems where instrumentation-based approaches are blind. Now, at Opsian, we had a customer who was using our production profiling tool, and they already had another APM tool in production. And they had this problem where every so often they would hit an HTTP endpoint on their system, and that would be really slow. It wouldn't be slow on every request. It would just be slow once every 5 seconds or so. bit weird, the kind of thing you want to kind of understand, because you don't want to leave your customers hanging there for 5 seconds getting frustrated. Now, the tool itself that they were already using was an instrumentation-based tool. So it instrumented HTTP servlet requests to see how much time those operations took up. And their tool said, don't worry, your customers are lying, you don't have any problems. I'm like, hang on a minute. We definitely do have problems because we can see it when we do it ourselves. What's really going on here? And it turned out the cause of their problem was actually that Tomcat kept a resource cache of all the different resources it had loaded up. It would expire that cache periodically and do a quick ask those different resources if they needed to reload. And one of those resources went, ha-ha, I know what you've given me. You've given me an opportunity to scan the whole class path of your application, which involved hitting the disk. It took a couple of seconds, and so would cause a big pause periodically when this cache expired. That's the kind of situation where if you haven't thought about it ahead of time, your instrumentation will be blind, because it can only see things that you've thought about instrumenting a priori, ahead of time, whereas something like profiling will not make that kind of assumption. It will let you see what's really going on. And the other problem I find with the kind of instrumentation-based approaches is really the overhead. It sounds really great to be able to just add this instrumentation around. You can see what's going on. You can bytecode weave in. And if you're careful, it can be great. But the more detail, the more information you want to extract, the bigger it becomes the bottleneck. The bigger your application, this helicopter, has to lug around the weight of the additional instrumented code and slow itself down, which is not great when you're trying to solve your performance problems or just improve your application's performance in general. Cool. Now, surely there's a better way, right? So we've talked about metrics, very useful, but good idea not to get carried away. We've talked about instrumentation, also can be useful, but again, you don't want to get carried away. But what about production profiling? How can we use profiling in production in order to understand these kind of problems? Sadiq, how about that?
Sure. So, how do we use a production profiler? The idea of production profiling is that we basically find the time period that we're interested in. We find the machines that we're interested in, and we then decide, well, what is the resource of interest that we're actually trying to profile?
Yeah, so the resource of interest here could be a CPU time resource, if that is perhaps where your bottleneck is. It could be a memory-oriented resource, if you have like a problem where you're running out of memory or you're having a memory leak. Find your biggest bottleneck, solve that bottleneck, and kind of redeploy and iterate. I think that's a good way of thinking about using any system that gives you production performance information. Now, I mentioned on the previous slide, or you mentioned on the previous slide, about the distinction between CPU time and wall clock time. What's going on here? Well, time sounds like time, but actually when you're looking at what time your system takes up, there's a few different views, a few different things you can think about in terms of that time. Firstly, there's the actual CPU time. So that's the time your code is spending on CPU, running instructions, actually doing work, right? And then there's the wall clock time, which is the time from the beginning of the operation to the end of the operation, the total time, including times where you're waiting for external systems, you're blocked waiting on I/O, or maybe you've just got a big thread pool and you're not scheduled on CPU at all. Now, I like to think of this in the form of a coffee metaphor.
And that's slightly because Richard is a coffee addict. He's even brought his own cute little cup from England because apparently it doesn't taste right if it's not in his cup.
Thanks. Yes, but I do like to think of a good coffee metaphor. Now, if you go to any good coffee shop, or even a Starbucks, you'll find that it's got a big queue in front of it. And if you're trying to get your coffee, you go into the queue, you wait to be served, you pay your money, you enter another queue when you're waiting for the barista to make the coffee, then you get your coffee coming out on the other end. And the CPU time here is really like the time taken when you're actually handing the money and they're actually making coffee, the actual time on CPU. And the wall clock time is the total time from beginning to end. So looking at wall clock time can be useful if you're trying to understand why you're blocked on a certain resource, why you're waiting for some disk I/O, waiting for an external system to talk back to you. But it can also include a load of other information that you just aren't interested in if you're looking at something that's actually CPU bottlenecked. So it could include loads of information that says, hey, your system's just sleeping around and doing not very much. So it's good to be able to measure and understand both CPU time and wall clock time. Now, once we've said, profiling get us information about what these resources are doing, how would you visualize that information? Now, the most simple way of visualizing profiling information is what we call a hotspots or a flat profile view, right? So hotspots is just a list of the methods in your application saying for each method, how much time is it taking up in terms of your system. Now, better hotspots views can also tell you what was calling the method at the time. They can also tell you what lines in the method are hot. But it's just a very simple flat view aggregated over that method, and quite good when you just want to see, look, what's the biggest bottleneck? What's really going on here? Now, if you want a context-specific view, tree views are another view that you can use. So a tree view takes the tree of all the method calls in your system and displays them laid out like that. So the top method would usually be something like javalang thread.run, okay? Because ultimately that's the thing that will be calling lots of different things in your system. And then whatever in the tree is a parent is a method that's calling its child. That's what the tree relationship gives you. And obviously it's a tree rather than just a list because methods can call multiple methods over time, right? That's how software works. Within the tree, you can also distinguish between, for example, self-time, time spent within a method, and total time. So that's time spent on that method and all its descendants in the tree. So that tells you, is it a bigger operation that you need to concern yourself here with, or is it just one specific method that's eating the time up? And then there's flame graphs, right?
Yeah, so flame graphs.
I love flame
graphs. So flame graphs are a visualization that's been championed by Brendan Gregg, who's an engineer at Netflix. And flame graphs are a way of visualizing the information that you've got from a profiler. This is actually not a flame, this is an icicle. Flames generally don't go downwards, but you can have them either way. So if you look at this, the flame graph, the x-axis represents the percent of the total samples we got that is at that particular, that has that method in the stack trace. So all methods all threads in this set of samples have come from Java lang thread run. That's where they start. So that's 100% of samples we saw there. Then if you keep going down, you'll see the next one. Basically, everything is in this this NIO acceptor. So again, that's the full width. And then as you go further, as the stack starts to split out, that's where you start to see smaller and smaller boxes. The width of a box is the percentage, as I said, of percentage of samples that we've seen that method in. The width of the box underneath, the difference between those two is the amount of self-time. That's the amount of time where samples actually ended in that method. So the amount of time that method was the one that was currently executing when we took the sample. So if you can see on the right there, for example, you've got a method with a huge amount of self-time where it's really fat and it's got one little child in that's tiny and narrow. So flame graphs are great because they allow you to basically take a whole bunch of profiling data, put it on the screen and have a visual look, and you can often see some of your biggest bottlenecks just visually by scanning that report. Right. So we've talked a bit about some of the other methods that we can use to gather performance information from our production system. Now we're going to talk about the actual kind of technical aspects of how do we go about actually profiling a JVM-based application in production. So the oldest types of profilers are what are called instrumenting profilers. Now Richard talked about instrumentation before. So what an instrumenting profiler adds instrumentation to the program under test to measure the resource of interest that we're interested in that we're trying to profile. So it might be memory, it might be CPU, it might be wall clock time, what have you. And so if we were looking at a wall clock time profiler, instrumenting profiler, what that would do is it would add instrumentation at the beginning and at the end of a method, so it knows when you've entered and exited a method, and then from that it could actually construct the call stack samples that you can then use to produce these reports. Now, the problem with an instrumenting profiler is that it modifies the application under test. right? The instrumentation it adds changes the behavior of the application under test. And it changes the behavior in a way that's not uniform across all programs, right? So it's not like we say that, instrumenting profiler adds 20% overhead to all programs. Some programs, it might actually add little overhead. Other programs, it may add dramatic overhead. So if we think about the execution time case, if you've got where you've added some instrumentation at the beginning and at the end of a method, if you've got a code base that's full of really, really small methods versus a code base that's just got a couple of massive methods, clearly the overheads are going to from instrumentation are going to be different between the two. So the impact it has on an application's performance is not predictable, right? And so it has high overhead, and it's also inaccurate because we don't know actually how much of the performance we're seeing is caused by instrumentation and how much is actually the actual program under test.
That's right. The nicer your refactoring is and the cleaner your code is, the higher the overhead instrumenting profilers end up being. Everyone in the room who's working on like a legacy monolith full of 1,000 line methods is going, yes, yes, it's good for me. But not if you've got nice clean code.
All right, so what else can we do? So we saw instrumenting profilers, and now we're going to look at sampling or statistical profilers. So what sampling or statistical profilers do is that they stop the application periodically and they measure the resource of interest. So if we were measuring execution time, for example, we would say, all right, every 50 milliseconds, 100 milliseconds of CPU time being consumed by this application, let's stop it momentarily and work out where it is. We'll record that and we'll carry on going. And you could do that same thing for memory. We'll stop after so many allocations or so much memory allocated. You could do it with disk I/O or network I/O, what have you. So this is a diagram up there for what an idealized sampling profiler would do in Java. So we've got this program that's currently running. You've got web server thread run, which is calling controller do something, which is then reading a person and constructing a person. This is the program moving along on the x-axis. Each of those green points is a point where we would basically stop the program and we'd measure what it's doing. So we'd get the current stack. So the first one we'd get would show us we're in web server thread run. The next one would show us we're inside the new person constructor. And we'd go on like that. And then what we would do is we would do this over a long period of time, and then we would aggregate those samples, and we'd have a statistical view of the program's performance over a period of time. So this is how an idealized Java profiler would work. And there's actually a call in Java called get all stack traces, which unsurprisingly gets all the current stack traces for all the threads running in Java. But there's a slight problem with using that to actually profile your Java code. And the problem is that, so who here is familiar with the concept of a save point? Right. So save points are a mechanism in the JVM by which the JVM can bring the application itself to a halt in order to do some kind of work. So it might be, the most common one's a garbage collection, but there's a whole bunch of other small housekeeping things that the JVM probably wouldn't want to do while the data structures they're manipulating are being concurrently modified by the application. So it actually pauses the application. And save points are essentially, the way they're implemented is at the beginning and at the end of a method, and also inside certain types of loops. There is instructions added that cause the application to read a little bit of memory. And it's the same location of memory each time, and the application basically reads those memories, so it's a very, very cheap operation. And when the JVM wants to bring the application to a halt, it unmaps that page that the application is basically reading that memory location in, and that triggers a fault, which means that then the JVM can then decide to do whatever it wants with that application thread. So it's a mechanism by which the JVM can bring application threads to a halt. And those save point polls, like I said, they go in the beginning, at the end of a method, and they also go in certain types of loops. There are some types of loops where they can be removed.
So by default, the save point poll happens on the head of, on the back edge of every kind of regular loop. So every time it goes around once, it does a save point poll. But if you have a integer counted loop, so something that starts off with like 4 int I equals 0, I less than n I plus plus, it will go, I can just optimize away that safe point poll. It'll finish the loop fairly soon afterwards. I don't need to worry about this. And remove those safe point polls, which can cause problems.
So we've talked about safe points. Now, why that's applicable here is that get all stack traces actually requires a safe point. Can actually require several safe points. And the JVM needs to bring all the application threads to a halt in order to actually get their current stack traces. Now, safe points interact with something else that happens in the JVM, which is inlining. So one of the optimizations that the hotspot compiler relies on is rather aggressive inlining. So an inlining is where when you've got one method calling another method, we can, in many cases, we can actually take the contents of the method being called and actually pull those instructions into the method that's calling them. And if you've got, especially for things like getters and setters, for example, you can remove a lot of the overhead of having to do that method call, right? Like you don't have to go and park off a bunch of registers and such like. And so actually it can be a massive performance win. When Hotspot does inlining, it also removes the actual safe point polls from the methods that it's inlining, from the entry and exit, those safe point polls. Now, the reason why that's a problem is that combined, that get all stack traces requires a safe point, and that combined with the optimization that Hotspot does for inlining, means we end up with a situation like we have on this diagram here. So we saw the nice idealized sampling before, and this is what actually happens if we use that method of profiling. So what we would do is each one of these little blue circles is a safe point poll. So you see the first green arrow that comes down here. That's great. We're in web server thread run. We got a sample that says we're in there. The next one, we should be in new person. Now, anything that's in purple is a method that Hotspot has decided to inline. So basically, Hotspot has decided to inline new person into repo read person, which is then decided inline into controller do something, and it's removed the safe point polls from those methods, which means the next safe point poll we actually have is not for a while. It's not until the end of the controller do something, because there's a couple other small inline methods here as well. And so what we'd actually see if we were using get all stack traces is that we'd see a sample at the beginning, and then we'd see a sample right at the end of controller do something, which would actually misattribute the actual time we spent in the new person constructor and in print HTML. So the problem we have with kind of a naive implementation of profiling in the JVM is that actually it's quite inaccurate. Safe point bias means that actually a lot of the reports that we could be getting and the profiles that we could be getting can actually have a significant bias in them. And the bias can get worse as well, because as Richard was saying, there are certain types of loops where safe points can actually be removed. And these loops can be quite long as well. So there's periods of time actually where we might actually be blind to the work that's being done for the resource that we're trying to actually measure.
And again, these are things where you're blind on areas where the JVM has more aggressively optimized. So things that you would expect to actually be really hot, really important code, that's where the blindness can get worse.
Right. And then we have another problem as well, if we're triggering safe points, and that is time to safe point. So this is a diagram. So we've got a Sybil system here. It's got 4 threads, and the first thread we hit a safe point poll. So we decided that we want to trigger a safe point. Right? These threads are executing. In the first thread we hit the first safe point. Right? Then very quickly after that, we hit the safe point, the second one and the third one. But the fourth thread might be doing something like it might have a loop that doesn't have any safe point polls in it for a while, and we have to wait until it gets to the end of the loop. And actually, that time between it doing that and the first thread stopping, that's wasted time in your system, and that's also latency that's being introduced. And interestingly, if you're interested in that kind of data, there's a JVM flag which is print safe point statistics that will tell you things like time to safe point. So with kind of naive profiling approach in the JVM, you could potentially you end up with a system that has significant bias in the data it gives you, but also that the actual performance implications of safe points mean that you're limited in the sample rate that you can actually take in order to that you can take. Sample too high a rate and you start introducing too much jitter and latency into your system, and the overhead becomes too high. But is there an alternative? Is there something else we could do? Well, there is. there is what's called what we call advanced statistical profiling. Now we talked about profiling. We talked about sampling profilers being take the program under interest, pause it at some point, capture what it's doing, and then let it run. Well, is there another way that we could actually pause it? Well, it turns out there is. Nearly all modern operating systems have this concept of operating system signals. So signals are a way that you can say to the operating system here, asynchronously deliver this message to this on Unix, this process. And the operating system will basically interrupt that process and will deliver on one of the threads of that process will actually trigger what's called a signal handler, a little bit of code that is designed to run in response to the process receiving that signal. So it turns out actually that you can do this with the JVM. You can trigger an OS signal. You can then have a signal handler that runs in a particular thread. That thread can actually capture the current running stack of the JVM and then exits the signal handler and then the thread continues running. But crucially, there's no save point. And only one of the threads actually ends up running the signal handler. And so you actually can do this with very, very low overhead. By choosing your sampling rate, there's no safe points that introduce jitter into the whole of your system. You can do it with very, very low overhead. And this is not a technique that's generally used by existing desktop profilers, because it's kind of hard to do with a desktop profiler. There are a bunch of open source profilers. There's things like Async Profiler. There's Honest Profiler, which was written by Richard here, that support this technique.
Mission Control also uses a similar approach, slightly different method internally, but a similar approach to gathering data as well here. So it can give you a low overhead profiling.
Okay, so if we have a way of doing low overhead profiling, and we've got some kind of some tools to do it with, why don't people do it? Well, one of the issues that we've discovered is that people tend to be put off as much by practical issues as they are technical ones. So let's look at some of the practical issues that are involved in ad hoc production profiling. So when we say ad hoc, we mean I've got a performance problem. I'm going to hook up a profiler and try and diagnose what the actual issue might be. Well, for one, generally requires developers to have access to production, right? If you're using one of these tools, you need to have access to a system, hook up to it, collect some data, download it, and then analyze it. Now, in a lot of businesses, developers actually don't have access to production. There's many sectors where there's very strict rules around that as well.
Sometimes in, for example, banking, you may have regulatory Chinese rules that stop people writing code and also managing the production system where it runs on, for example. So it would be literally illegal to connect a profiler up as a developer in that environment.
Right, and the process generally involves manual work. You've got to actually collect the data, and then normally run something, a reporting tool over it to generate those kind of reports that we saw earlier. And lastly, the open source profilers support the low overhead profiling, generally are commercially unsupported. So is there a way that we could kind of get around these issues? Well, what if we have a low overhead way of profiling that's low enough that we really don't care about it? What if we just profiled all the time? Could we avoid some of these issues? Well, we wouldn't need to have access to production every time there was an issue, because profiling would always be on. You wouldn't necessarily need to spend time manually doing reports, because now you're collecting all that data all the time. You should have an automated way of doing that, right? And does it open up any new capabilities to us? Well, it turns out it does. So one thing we get is historical data. If we're profiling production all the time, then it means that we can start doing things like, well, my CPU core's pegged at 3 a.m. last night, right? What happened? Well, we can go back and we can look at it. And also, it allows you to do the problem you've got with ad hoc production profiling, like ad hoc profiling only when you have a problem, is you're only looking at your system when it's pretty sick. How do I know that I'm looking at this profile, and actually, how do I know what normal is? Well, if you have historical data, we can kind of understand what normal is. We can say, okay, well, we've just pushed a new version of our software to production, and it's slower than the previous one. Users complaining. Can we compare the two? Well, yeah, you can, because you have the historical data, because you've been collecting it. We can also start putting our samples in context. So we talked about the different applications versions that we have, where you could attach those to the sampling data you have. You could attach environmental parameters. So this is an Amazon C3, and this is Amazon C4. And you can ask questions like, how do my C3s compare to my C4s? How does my Java 9 instances compare to my Java 8 instances, for example? And that's something you don't get if you just do ad hoc profiling. And that's basically what we do at Opsien. That's what motivated us. So Opsien is a continuous profiling platform. We have our own commercially supported Java agent that uses that advanced statistical profiling technique, amongst others. They run on your JVMs. They send the data to our service, which basically indexes them, aggregates them, and then makes all the reports available to you in real time for the different reporting types that you've seen. Google actually also have their own internal system that does this called Google-wide profiling. I highly recommend Googling that. They have an article they wrote about why it's done so well for them. It's definitely worth a look. So in summary, we can profile all the time in production with very low overhead. We can overcome a bunch of the practical issues that we have by actually just doing it all the time. And if we do it all the time, it opens us up a bunch of new capabilities.
Fantastic. So let's wrap up what we've talked about in this talk as a whole. We started off talking about how performance mattered to businesses. It was important for keeping your customers happy. It was important for keeping your infrastructure costs low. It was important for running a reliable service. But development and production environments are not the same environment, right? Optimizing something for a synthetic workload on your laptop won't necessarily help you understand the same problems that you have in production. Metrics are very useful for narrowing down these problems, but they can sometimes be hard to action. They don't tell you what's the line of code I need to fix. Instrumentation, again, useful, but can have high overhead. Continuous profiling is a really useful approach that's really complementary. I don't want to say just do this and don't do anything else, but it's a really useful approach to be having really good capability to have. We think that we need a bit of an attitude shift on profiling and monitoring in general, a way of thinking about these problems in a more cohesive and more all-encompassing way. So that's got a few different parts. Firstly, it's thinking about these problems as a systematic problem rather than an ad hoc problem. So as opposed to only investigating and dealing with these problems when you actually have a genuine problem, when the problems are happening in production, we want to think about things ahead of time. That doesn't necessarily mean spending loads of time optimizing for problems you don't have. It just means thinking about what tooling you get in place, what things you can measure. Are you ready for when these problems happen? Have you thought about your overall system designs? Another aspect of that. Being proactive and not reactive, so getting ahead of the curve in terms of avoiding these problems and getting ahead of the curve in terms of measurement and understanding what these problems are, rather than just reacting or fighting the last war. Things like performance tests, replicating previous performance problems, they're often a very reactive approach, fighting the last war. And continuous profiling is a really useful way of doing that. It's the way to make profiling incredibly valuable on your production environment. Okay? If there's one takeaway, it's please do production profiling all the time. As I said, Sadiq and I run this business called Opsien that provides a continuous profiling product. So if you've got any questions about that, please come and have a chat with us afterwards. We're pretty much out of time, so probably best if you come and talk to us at the end. But thank you very much. You've been a great audience, and I hope you found it very interesting.
Thank you.